Well, good morning, or good afternoon for some of you.
Hello.
All right. So I guess I left you thoroughly confused Monday. Let's try to get some practice in that will clarify this. Just the high points. We have the BNF definition for lambda calculus expressions. We have expression can be a variable or a function. How do you know it's a function? It starts with lambda. Lambda, variable name, dot, expression, or application, expression 1, expression 2. So those are the things. What are the operations? The operations are the rewriting rules, alpha reduction, beta reduction, and eta reduction. We're not going to worry too much about eta reduction, but the alpha reduction, we're allowed to change the variable names in an expression, as long as we change them consistently and don't change the structure. And then the beta reduction is how we apply a function to its input. And I'm just going to do some examples right off the bat here. I've got some in here. So the beta reduction rule is remove the lambda x dot, substitute every occurrence of x in expression 1 with expression 2, remove expression 2. So if I use good old Notepad, and I'm just going to use capital L for lambda since Notepad isn't clever enough to do lambda. I can do lambda x dot x plus 1. Now, is that a function, first of all?
Yes.
Yes.
Because it has the lambda variable name dot and then some kind of an expression. And as always, we are pretending that with that, we're pretending that we have numerals and we're pretending that we have math operators. We'll get there. Okay, now if I put another expression in here, like 6, right, that's just a value, then I have an expression followed by an expression. There's the first expression right there, and there's the second expression. So since I have an expression followed by an expression, I have application. And since the one on the left is a function, I can use the beta reduction rule. And the beta reduction rule says this: get rid of lambda x dot. Just get rid of that. And then everywhere in here, this x plus 1, everywhere you see an x, replace it with a 6. Oh, that's no good. And then from there, we can resolve that using normal math, even though we haven't invented normal math yet. So that's the basic rule. Now, the details of it can get messy because, you know, we can have more sophisticated expressions than this, but that's the basic rule. If you are applying a function to an expression, an operator to an operand, you can use the beta rule to get rid of the lambda x dot and then replace every occurrence of the x or whatever variable you have with that expression. Here, the expression happened to be 6. What if the expression was not 6? What if it was y? I would end up with y plus 1. Can I go any further with that? No. So that's the answer. That's as far as it goes. It's reduced as far as it can go. Basically, reduction, when something is reduced, it means you have no more alpha or beta rules that you can apply. Now, let's talk about the form of these things. Remember, free and bound variables. Is x in this expression free or bound?
Bound.
Bound, because that's the variable that we're saying is the input or the argument to the function. So it's bound. What if I change this to there? So the X is bound. Is the Y bound or free?
It's free.
It's free. So what if I did this? Dun, 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 dun. I want to make this, I'm going to do this a little bit more. So these parentheses look like this, okay? And then I'm going to apply this to two numbers, 5 and 7. Now it's a little more complicated because we have these, these two, a function, but the function, it contains another function. Okay, how do we handle that? Can we use a beta rule? Do we have an expression followed by an expression? Let's see. Here's an expression, right? Even though it's starting to look a little uglier, that's one expression. And there's an expression, so I have an expression followed by an expression. Is the one on the left a function?
Yes.
Yes. And the one on the left is a function whose first input is y. You always work from the outside in. So the first input is y. And then this is an expression, so I can use the beta reduction rule, which means that I'm going to put the 5 in there. But should I put the 5 in there to replace the x, or should I put the 5 in there to replace the y? It's going to be, you work from outside in. So
Wow.
replace the y, right? So now this thing becomes Lx. I get rid of the Ly dot. And it's x plus, and we replace every occurrence of y with 5. And then I have a 7 out here. Now, can I do that again? In other words, do I have another system application where I have a function on the left and something, it doesn't matter what, on the right? And the answer is yes. So I can do that again. I do beta rule again. I get rid of the Lx dot and I replace every occurrence of x with 7, and I end up with 7 plus 5, and we can resolve that to 12. What if I did this? I'm going to get rid of that plus sign. Does that change anything? In other words, here I've got lambda y, lambda x, xy. No plus sign, that's just expression followed by expression. And then I have 5 and 7. Can I still do this substitution where I substitute y, 5 for the y that's in that expression?
I think so.
Yeah. Now again, and this is, see, you're probably thinking, and so I'm encouraging you to stop. What's the rule say? The rule says if you have an expression on the left that is a function, and you have an expression on the right, you can blindly and mindlessly take the expression on the right, get rid of the Ly dot, and everywhere you see a y in the expression, you replace it with whatever the operand is, which in this case is 5. So we can do that. And now we have the same situation as we had before. We have an expression on the left and we have an expression on the right. And the expression on the left is a function, so we can use the beta reduction and we can replace, get rid of the Lx dot, and everywhere I see an x in here, I replace it with 7, and I'm left with that. Now I'm done. I have a 7 and a 5, that's application, but the one on the left is not a function, so I can't use the beta rule. I can't do anything. And that's okay. That's an answer. That's a value. The value is two numbers, 7 and 5. the computations don't have to make sense because there is no sense in computation. There is no meaning in computation. I'm going to swap these around. And I'm going to change that 5 to that. Can you see any situation where I can do any kind of a reduction here? Let's see. Do I have an expression? How many expressions am I dealing with here? There's 1, there's 2, there's 3. And I have an expression followed by an expression. So I could do, maybe I can do a beta reduction if the one on the left is a function, which it is. Now I also have this situation. I have an expression followed by an expression where the one on the left is a beta, is a function, so I could do the beta reduction. You work from left to right, and if you need to enforce any precedence, you do that with parentheses. So before, when this was just 5, remember when this was just 5? You guys said, what? Take that 5 and get rid of the ly dot, and then we get lx dot 5, 5 and x. All right, that's what we did the last time. But now it's not 5, it's something else. So what do I do?
Replace it mindlessly.
Exactly. Whoa. Replace it mindlessly, right? So it doesn't matter how complicated that thing is. Think of it as just one entity, like it was the numeral 5 or the variable p. So now I've got that in there. How did I get that in there? I took the operand or the argument to the function. The function is a function of y. So everywhere that I see a y in the expression, I replace it with that. Once I get rid of, I'm going to do an intermediary step there. Once I get rid of the ly dot, I just have this. So what we're saying is everywhere I see a y in this expression, I need to replace it with the lt dot t plus t. And that's what this looks like. Now can I do it again? I've got an expression, and I've got an expression. The one on the left is a function of where x is the input argument, and the one on the right is the operand. So we're going to apply that function of x to the argument of 7 and follow the same rule. We get rid of lx dot, which leaves us with lt dot t plus t. And then everywhere I see an x, I replace it with 7. There's only one x in there. Can I do it again? Yeah, now I've got a function of t being applied to 7. So I get rid of lt dot. Everywhere I see a t, I replace it with a 7. And because we're pretending math exists, we can resolve that. Is the process, the pure, forget that it doesn't mean anything, process of rewriting starting to become a little clearer through examples?
Yes.
Yeah.
One, at least for one of you. Okay, for two of you. And that's the way you get better at it, right? Is you look at these examples over and over and again and try them. Now, here's what's interesting about this one, though. Normally, when you think of a function, you think of the arguments that come into the function as being values that are not in and of themselves functions. But notice what's happening here. Because I don't care what the expression is, I just mindlessly take whatever that expression is and plug it into the function on the left. If that expression happens to be a function, I now can have functions that are input to other functions. And in your programming experience, you don't experience that very often. Programming languages tend to treat data and functions as separate things. However, some programming languages, they're called higher order languages, allow data and functions to be treated as the same thing. So you can pass a function around just like you passed a data value around. Instead of passing a pointer around, you pass the function around. And that's what you just saw here. We actually allowed a function to be used as input to a function. Because again, the beta reduction rules don't care. They just say, here's a pattern, replace this pattern with that pattern. This is very powerful. This is what gives the Lambda calculus its ability to describe all the different computations. And again, not only that, I'm warning you or giving you heads up on how functional programming works, and functional programs rely on this quite often, where you can build up complex functions by having functions that not just call other functions, but actually functions that accept other functions as arguments. So function composition is really what we're doing here. And as we start to get into more sophisticated things, we'll see how this works. Now, if I took that, let's see, let's do something else. Now, because I can do that, let's say I did lx.ly dot y, I'm sorry, x, y, y, like that. And then I apply that to LT dot t plus y. Okay. Now, is this x bound or free?
I might be wrong, but
Go ahead. That x is bound by this x, because this x out here encompasses that entire thing. Now, you're right. If I only had this,
right,
if I only had this, within the scope of this, x is free, right? Because it's in a larger scope, it's bound out here. It's bound at the outer layer.
okay.
Okay. How about the y's? Bound or free? In here. Those are bound, and they're bound at that more local level. And how about the t? Is it bound or free?
Bound.
It's bound to that t. And how about this y? Is it bound or free?
Free.
Free.
Free, because it has nothing to do. These two expressions are completely independent, and this is the only thing that are bound in here, since it's lambda t dot, is going to be a t. So it's free. So this y is free. Now let's keep that in mind and do the same trick that we did before. We're going to take now, and this is a expression. They're starting to get uglier, right? There's an expression followed by an expression. we can use a beta reduction rule if the expression on the left is a function, which it is, and it's a function of x. So we're going to put the function of x in, and we get ly dot. Everywhere I see an x, I replace it with lt. T plus y. Oh, that's not good. Y. Okay. Now, let me ask this question again. Is that y, is it now bound or free?
Oh, it's bound.
Now it's bound. This is a problem because it should be free. This is what we call accidental capture. Accidental capture. It just happens to be, just by coincidence, that this was a function whose variable was named y, and this one happened to have a free variable. And remember, structure matters. So it's a free variable who happened to be named y. And by doing the beta reduction, it just coincidentally binds that variable, which violates the structure. So this is where we have an opportunity to use the alpha reduction. The alpha reduction says you're allowed to rename variables as long as you don't change the structure to avoid accidental capture. So I'm going to do an alpha reduction to rename that to S. And then did I change the structure? Let's see. I've got LT, and then I've got T plus some other variable. And then I've got LT and T plus some other variable. It just happens to be that in the original case, we called that some other variable Y. Now we're calling it S. But in terms of structure, these are structurally equivalent, right? So that's all we care about. And now, when we do the beta reduction, it comes in like that, which is what we wanted, right? We wanted to have the Y's are properly bound as they were previously. The T is bound to this local lambda T, and then this S is free, which was how the structure was supposed to be. So that's why you use an alpha reduction instead of a beta reduction, to avoid this accidental capture. By the way, can I reduce this anymore? Let's see. In order to do more, I'd have to have something out here, right? So I don't have anything else out here. How about inside the parentheses? Can I do anything inside the parentheses? Can that be resolved at all?
Substitute the T.
Yeah, we can do the beta reduction here because we've got a function applied to an argument. And so we get ly dot, and then if I do this, it will be y plus s. Why am I doing capitals? Y plus s, and then y. And it doesn't have to mean anything, which it doesn't really. I don't see a good meaning there. That's the rule. We're just following the rule. So you're allowed to do, again, think about scoping rules. If you have an operation inside of parentheses in algebra, aren't you allowed to perform that operation? It's the same trick here. If you don't have parentheses, you go left to right. Similar to, precedence in algebra. Okay. It's okay to have an ugly result. That's a value. That's an expression. It's a value. These terms get very rubbery. We always like to have, what's the answer? 12. Well, that doesn't always happen. And you experience that in your calculus classes, especially when you did, it used to be in algebra, you would get, your answer was a number. And then it turned out your answer was a function. And then in calculus, your answers became families of functions when you did integration, because you couldn't say what the constant was, right? When you integrated something. So your answer became families of functions. So things get more and more abstract, and it's still considered an answer or a value. Okay, let's see. Do we need to do any more of these? Oh, yes, let's do one more thing. I'm going to take this example and do something slightly different. I'm going to do that. Because once you have multiple variables, this thing can get ugly. So this is shorthand for that. And the scoping still applies. You go from the left to the right, that's considered outward in. And then I can do something like, it's supposed to be at times. Yeah. Which we could rewrite as that, right? And then out here, let's put a 10. So what's the first thing that I can do, if anything? Do I have any situation where I can use a beta rule?
Substitute S for that.
Right. So here's an expression followed by an expression. The one on the left is a function, so I can use a beta rule. Here's an expression followed by an expression. I could use the beta reduction there, but remember, we go left to right. So I'm going to go left to right, and I'm going to take this expression, and wherever I see an X on the expression on the left, I'm going to replace it with that. So I get rid of the LX, or I get rid of the X, and then I replace that X with that. I can do it again now, right? I've got this function of y applied to 10. And so I can do another beta reduction. And then I get rid of the ly dot, which leaves me with and then I can do it again. I've got a function of s, which is embedded a function of t. So that first 10 goes in for the s. I get rid of the s. And then I can do it again. I get rid of the LT dot and I get 10 times 10. And because we know what math is, we can resolve that. I'm pretending that numbers in math exist. You see how this can start to get sophisticated and complicated. We won't get too far along in this. I said that if you did something inside of parentheses, that's legal because that's precedence, right? You're always allowed to, again, think of algebra. If you see something inside the parentheses, you're allowed to do those operations and then worry about other operations. What would happen if you took advantage of that and did the inside the parentheses first? Would you come up with something different? Well, we do ly, and I'm going to take this and apply it to the first argument, and that gives me LT dot y times t. And then I get ly dot, and now I'm getting rid of the LT dot, and I have y times y. Apply to 10, and then I have 10 times 10. Same thing. Is that legal? Did that resolve in, say, accidental capture? Perfectly legal, because the parentheses are showing precedence. This is good news for you. As long as you're following the rules, you cannot make a wrong decision. You'll always get to the same answer. It's called the diamond property because you can take different paths, but you always end up at the same endpoint, as long as every path was legal. Okay. One more example. Let's do L, X, Y, Z, X, Y, Z, and then L. I've got a function that requires 3 inputs. I have 3 inputs over here. There's the first one, second one, third one, so that's going to match up. And the sequence in which I do them, I take the first expression LPQ.P plus Q is going to be, you can see where this is ending up, right? It's going to be 5 plus 7 by the time we're done. LPQ.P plus Q, and that's going to go in for X. I work from the outside in or from the left to the right. So I get rid of the X. I replace the X with whatever that expression is. And then I'm going to apply that to a 5 and a 7. And then I'm going to do the same trick for the Y. So I get rid of the Y. This will be easier this way. I get rid of the Y and I replace the Y with a 5. And then I get rid of that. And then I get rid of the Z and I replace the Z with a 7. And then I can keep doing this. Now I've got a function with 2 arguments and I get LQ. Oops. And then I just have 5 plus 7. Okay. Notice, by the way, there were lots of options because inside the parentheses, I could have done things differently. I'm not going to go through it here, but you might want to walk through an example like that and convince yourself that had you chosen to work inside the parentheses at first or at any time during this series of beta reductions, then it still comes out the same. As long as you're following the rules, it's okay. What would not work out is if you did that first. And the reason is you're violating the left to right rule. Okay. Now, this is a remarkably simple system once you learn to trust it. It is confusing and it's notationally horrific, but it's so simple. It's so small. I mean, where is it? That's it. That's the system basically, with the beta reduction, the alpha reduction. And yet, it does cover all computation. So I've been pretending that we have numbers. And so now let's get numbers. We've gone through these kinds of things. All right, so here's how you get numbers. You find a pattern and you just call that pattern 0. You invent a pattern. And then you find another pattern and call it 1, and another one and call it 2. And ideally what you want is if you can apply a particular function to the pattern that you're calling 0, and you get the pattern that you call 1, then that's effectively your add 1 function. That's your successor function. So if you can define 0, then you can define 1 as the successor to 0, and 2 is the successor to 1, and 3 is the successor to 2. So if you could develop these patterns where a particular function, the successor function, applied to 0 gives you the pattern that you're calling 1. And if you apply the successor function to 1, you get the pattern that you're calling 2. If you could do that, then you would have numerals and you would have the add 1 function. And as you know, once you have the add 1 function, you get all of mathematics. So here's the pattern. 0 is defined as lambda sz dot z. I believe the S was purposefully chosen to give you a mnemonic for a successor function. Z purposefully chosen to give you the mnemonic for 0. So sz dot z. Which, by the way, if you follow what that function does, it's a function of 2 arguments, right? It's a function of 2 inputs, s and z. If you put something in for s, you immediately just throw it away, and then you have the lambda z dot z left. 1 is the same thing, but with this s in parentheses outside of the z. And 2 has 2 s's outside of the z. And 3 has 3 s's outside of the z, and so on. And what this really is, you can interpret it in your head, even though this is mindless, you can still assign meaning to it, where that's the successor. 1 is the successor to 0, and 2 is the successor to the successor of 0, and 3 is the successor to the successor of the successor of 0. You get where I'm going. Lambda calculus loves recursion. So if we could only find a method to make that pattern work, which of course was done. So what was happening in the 1930s is people were coming up with all these clever patterns and methods. I don't know if you guys are familiar with the game of life. You can Google it and find examples of it and play with it. But people do the same thing. They find cool patterns in the game of life, and then they publish them or post them. The game of life, incidentally, has also been proven to be fully computational. You might need to look up Conway's game of life. Okay, so now we have math, and here's how it works. We have this thing called the successor function, and boy, is it ugly when you first look at it. After you look at it a while, you realize it's just a cheap trick. It's got 3 inputs, wi, and all it does is it repeats wix, but then it puts this y outside in parentheses. And what did we say the 1 was? It was going to be an s outside the 0 with a parentheses. So that's where they're getting that. They're just sticking that out there. So if we follow through with this, and we do allow this this notation, so you don't have to write the complicated forms all the time. We're going to say that is equivalent to capital S, and 0 is equivalent to this. If I bring that back up on successor function applied to 0 is equal to lambda, what did I say, wix, y, wix, and we're going to apply that to 0, which is sz dot z. Make sure I get that right. Okay. Which means if you follow along, then I have a function applied to an argument. And the first thing we're going to substitute in therefore is the y. So what do I get? I get the w. Get rid of the w. Now we have x, yx dot y, and then like that, which doesn't look like much yet, but I have a function of 2 arguments, and I have 2 arguments inside the parentheses, so I can start to resolve that. Oops. Lyx dot y, and then L, get rid of the s, ignore it because there is no s, right? So it's just x like that. Do that again, Lyx dot y, and now I'm going to apply this x to lz.z. That's the identity function. All it does is you put something in, it gives it right back. Now remember, we're only caring about form. We don't care what the actual names of these variables are. So I could, having trouble here, sorry. I could replace the y and the x with s's and z's if I wanted to, and I get sz dot sz, which we said is what we're going to call 1. How cheap is that? Now, do you think we can get 2? If you apply the successor function to this pattern that we're calling 1, you get the pattern that we're calling 2. And if you apply it to the pattern that we're calling 3, you get the pattern that we're calling 4. And after you look at it a while, you realize it's just a cheap trick. Because this thing is going to take in 2 arguments and throw the first one away and just give you the second one back, this mess inside here is always just going to resolve to x. And because that first step that we did puts that y with the parentheses outside of that, well, this thing is always going to resolve to x. And we get an additional y in the parentheses outside every time we do the successor function. So what we're always doing, every time we run the successor function on something that is something parentheses z, basically we get that back with an additional layer of s parentheses on it. Now it's framed in terms of x's and y's in this equation, or I'm sorry, in this formula. That's just so we don't do accidental capture, but we can always convert back to s's and z's if you feel more comfortable with that at the end of the day, because as long as we keep the structure the same, the actual variable names don't matter. So we really can say now 1 + 1 is 2. Now, if you apply the successor, this is what if you apply the successor function to 1, there's the 1. Same trick occurs. You're going to get this additional y on the outside. You know what this is going to turn into. It's basically going to turn into just the z with the y on the outside already. And so now we have y(x), which we can translate to SSZ if we choose to, and now that's equal to 2. It's kind of weird because I've never seen until lambda calculus, or until I was introduced to lambda calculus, I've never seen anybody actually prove that 1 + 1 was equal to 2. But in this system, you can prove it, assuming that you're all agreeing on what these representations are. The Rojas paper that I put up, which I think is a very good reference, I wrote my own notes knowing that I would never get as good as what the Rojas guy wrote. But if you look in there, he extends this to just generalized addition. Not only can you do the add one function, you can do 2 plus 5, whatever. So you get generalized addition. And from there, I believe he goes into multiplication. We're not going to. We're not spending enough time on it to do that. Okay, so I'm going to pause here, and then on Friday, rather than office hours, let's finish up the other two parts of this. In order to have a programming language, you basically need 5 types of statements. You need the declaration of the variables, you need assignment of values to variables, you need selection like if then else, you need repetition like loops or recursion, and you need IO. We're not going to worry about IO. But if this system is going to be fully computational, it needs to have some kind of assignment of binding of variables to values. Well, what you're seeing is rather than using strict binding of variable to values, what they do is they have functions that return values, and they return them to other, those returned values can be inputs to other functions. What we haven't seen yet is any kind of selection. We haven't seen if then else. So what I want to do on Friday is show you the development of the Boolean system, that this covers Boolean math. We'll define true and false, and then do some simple operations like true plus true is really equal to true. True plus false is really equal to true and false, or truly equal to false. So we define true and false, and we define and or and not. And then the last thing, in order for this to be fully computational, is that you have to have repetition of some form, and we'll walk through the recursive forms. There is no for loop, while loop type structure in the Lambda calculus. The only repetition you get is recursion. So let's plan on that for Friday. Before we go, I'm going to pause for questions or gasps of amazement that this simple system can cover addition, or whatever you need to share at the moment.
I have a question on the 10th assignment.
Okay.
It's not actually posted, right?
Yes,
Since
right.
there isn't. Okay.
Yeah. All right, so I'm going to fix that. I'm hoping today, it might be tomorrow, and then it'll be due, I'm thinking Wednesday of next week. I think it's helpful for y'all to have a little extra time to play with this new system. It is foreign in the sense that people haven't seen it before, not that it came from a separate country. Other questions? Okay, if you have them, this is a great place to use the discussion section for the module. And I've been better about keeping my eye on those discussions. So, all right, I'll see you guys Friday, and instead of office hours, we'll finish up this module, and then be prepared to get into functional programming next week with Dr. Racket. You know, download the Dr. Racket toolkit. You can look up Racket help guides, you know, Racket language. I would actually look up, if you can find something called the Little Lisper, L-I-S-P-E-R, the Little Lisper. The Lisp programming language was the grandparent of Racket, and they made a really nice little helpful introductory guide called the Little Lisper. And then from there came the language scheme, and they rewrote the Little Lisper and called it the Little Schemer. And both of those, I think, are really intended to be super simplistic introductions to functional programming. The tutorials that I've seen for Racket, I have not been so thrilled with, but I'll create, you know, we'll go through that kind of stuff next week. So this will get directly applied to Racket. Okay. All right. I will see you on Friday then. Have a wonderful day.